Welcome to the 50th lecture of this open course on diffusion in multi-component solids. Now that I have introduced you to ternary isotherms in the last class, I would now like to start with studying multi-phase diffusion. In single phase diffusion, we had diffusion couples with terminal alloys having the same phases to start with, and even during the course of diffusion there was no second phase developed within the diffusion zone. So, the simplest system for the case of single phase diffusion is when there is a complete miscibility. So, if we consider an isomorphous type of phase diagram, and if we assemble a diffusion couple between pure A and pure B at a constant temperature which is below the melting points of both A and B, we know that this would be a single phase diffusion couple. So, this is the initial contact plane x naught. To start with, we had on the left terminal alloy the B concentration was 0, on the right terminal alloy B concentration is 1 or 100%. Similarly, on the left terminal alloy the concentration of A is 1, and on the right terminal alloy concentration of A is 0. After the diffusion annealing at constant temperature, we know there will be a continuous concentration profile developed like this. This will be an error function type of profile for both the components. What happens if there are more phases existing in the composition range of pure A and pure B? So, again the simplest of it is a eutectic system. So, let us draw a eutectic system with some solubility on both A rich side and B rich side. So, if I consider a diffusion couple between pure A and some alloy with composition XB1 at a temperature at which XB1 exists as single phase alpha. This is still a single phase diffusion couple, because as the diffusion starts there will be again continuous profiles developed and there is no formation of new phase at the diffusion annealing temperature being considered here. So, again if we draw, to start with Cb minus was 0, Cb plus is, let us say Xb1 is 10 mole percent of B. So, this will be 10. The concentration profile would be something like this after diffusion annealing. This is x naught plane. For B, for A we had Ca plus is equal to 100 and Ca minus is equal to 90, and again the error function type of profiles will be developed for both A and B. But what if at the same temperature I assemble the diffusion couple between pure A and pure B here? Now, how would the diffusion structure look like? What is the diffusion structure? It is nothing but the microstructure that is developed within the diffusion zone. For a single phase diffusion couple, diffusion structure is simple. There are not many features because it is all single phase. So, at the most you can see some grain boundaries if they exist, but no precipitate or second phase. In multi-phase diffusion couple, the diffusion structure is interesting and it does give lot of information about phase equilibrium. There may be multiple single phase layers, there may be a 2-phase region or a 3-phase or multi-phase region depending upon how many components we are considering and so on. So, in this particular couple A B, how would it look like? The diffusion, how would diffusion structure look like? So, let us try to draw the concentration profile again here. So, obviously, in this case A and B both have different phases to start with. So, on the left terminal alloy I have phase alpha, right terminal alloy I have phase beta. So, there has to be an interface between alpha and beta. So, let us denote this interface here as xi. Now, it has to be noted this xi, the interface position is not necessarily same as the metanoplane position x naught. We will talk about this in the next class, how to determine x naught for this, but just remember now that xi is not same as x naught. Xi is the interface position, that is where the alpha transits to beta within the diffusion zone. Now, let us consider the diffusion concentration profile for B. On the left terminal alloy we have Cb minus equal to 0, right terminal alloy Cb plus equal to 100. We know as we enter the diffusion zone from left side, in the terminal alloy Cb is 0 and then the Cb will start increasing and it will increase until the interface position is reached. What is the concentration of B at the interface? Now, there are two sides for the interface. On one side there is phase alpha, on the other side there is phase beta. If we want to determine the equilibrium compositions at temperature T in the 2-phase region, we draw this tie line which I have already drawn here and I mark where the tie line intersects the 2-phase boundaries. So, this tie line intersects at position A and B here, and A represents the maximum solid solubility of B in alpha at temperature T. And so, the concentration of B in alpha cannot exceed the concentration A, and so at the interface on the alpha side this concentration is A, and we call this as C B at the interface in the phase alpha. Similarly, if we come from the right side, in the right terminal alloy, the concentration of B is 100%, and as we go towards the diffusion zone, B will decrease, and we know the minimum amount of B that has to be there in beta at temperature T is given by this point small b here. And so, where the concentration profile intersect this interface position, this concentration is corresponding to this point B here, and we call this concentration of B in beta. So, as we can see, there would be a discontinuity in the concentration profile at the interface. So, you have alpha on left side, beta on right side, and a planar interface between alpha and beta. And on the concentration profile there will be a discontinuity. The compositions on the two sides of the interface, that is A and B here, represent the equilibrium compositions of the two phases. We can assume local equilibrium at a planar interface, and this is very important because it helps us in determining phase diagrams from the diffusion couple experiments. If we get planar interface, we get the two phases which are in equilibrium, and we exactly get the tie lines between those two. Now, the question is, we see a two-phase region on the phase diagram here, but when I draw the concentration profile or the diffusion structure, I did not show two phase region, and the reason is because this is a binary system. Again, if we apply Gibbs phase rule, F is equal to C plus 2 minus P, and since I am considering constant pressure and the diffusion couples are isothermal couples, that is at constant temperature, so I can ignore this factor 2, which are basically for pressure and temperature, and I can write the maximum phases that can exist P max is equal to C minus the minimum degrees of diffusion couple requires at least 1 degree of freedom, that is concentration gradient, otherwise there would be no diffusion. And so F min is 1 for diffusion couple, and for a binary system we can see the maximum phases can be 1. So, in the diffusion zone of a binary diffusion couple, only single phase layers can form. There may be multiple single phase layers, but there may be multiple single phase layers within the diffusion zone, but in a given layer there will exist only one phase. Two phase layers cannot form because of the constraint from the Gibbs phase rule. Also, the interface between the two different phases formed in a binary diffusion couple, which is annealed at constant temperature, has to be a planar interface. What happens if the interface is non-planar? Non-planar interface may look wavy like this. Remember, when I say an interface, it is the cross section, or it is the plane parallel, it is the plane perpendicular to the diffusion direction, which in this case is the plane going into the plane of paper. So, if I take a cross section along this wavy interface or non-planar interface, and if I see the cross section this way, it is actually a multi-phase region there in that plane. And again, a two phase region or multi-phase region is not allowed in a binary diffusion couple, and hence a non-planar interface is not possible in an isothermal binary diffusion couple. In a ternary diffusion couple, obviously P max is equal to 2, and hence we can have a two phases are possible between two single phase layers. So, if we take a cross section along this non-planar interface and see its microstructure, we will see that there will be two phases existing in that plane, and two phase layer is not possible in an isothermal binary diffusion couple, and hence a non-planar interface cannot exist in a binary couple. Now, for ternary it is possible, because for ternary P max is equal to 2. So, a two phase layer can form, or there may be two single phase layers having a non-planar interface between them. So, this is possible in ternary diffusion couple or even in quaternary or higher order systems, but not in binary diffusion. So, this was about binary multiphase diffusion couples. Now, let us look into ternary multiphase diffusion couples. If I consider a ternary isotherm in which there is a big alpha solid solution region, similar to what we have seen for copper nickel zinc system last class. There is also a beta phase region here, let us say. Now, if I assemble a diffusion couple between two alloys which lie completely inside the alpha phase region let us call this alloy 1, alloy 2. Suppose alloy 1 has composition of and alloy 2 had composition of 50B. We know this will be a single phase diffusion couple with a nice S-shaped diffusion path, and all the concentration profiles will be continuous. So, there will be no discontinuity in the concentration profiles. So, if I draw this concentration profiles here, this is the initial contact plane x naught. I know to start with B is 30% on left side. So, Cb minus is equal to 30, Cb plus is 50, then Ca plus is 60, Ca minus is 60, and Ca plus is 20, and Cc minus is 10, whereas Cc plus is 30. So, after the diffusion annealing, there will be nice continuous profiles developed, something like this. However, if we form a diffusion couple between, let us say, alloy alpha 1, and beta 1 here. So, to start with, the two terminal alloys have different compositions in the diffusion zone, or there may be a planar interface between alpha and beta. So, again, for mass balance, the diffusion path has to cross the straight line joining the two alloys at least once. So, this diffusion path may look something like this. The way the diffusion path passes through the two phase region, the diffusion structure may be different. There are certain rules that help us to correlate the diffusion structure that is developed in the diffusion zone of an isothermal ternary diffusion couple with the features of the ternary isotherm. So, let us look at those. So, the first rule is that if there is a planar interface developed between two single phase layers in a ternary diffusion couple, it indicates that the diffusion path is passing through the two phase region along a tie line. If so, let me draw another type of isotherm here to understand this. So, let us say there are three single phase zones here. On the A rich side we have alpha, B rich side we have beta, and C rich side let us say we have gamma. There will be a three phase region or tight triangle. Say if I assemble a diffusion couple between alpha 1 and beta 1, and if I see a planar interface after diffusion annealing between alpha and beta, this is the interface position xi. That means the diffusion path is crossing the alpha plus beta phase field, which is this phase field, along a tie line. So, the tie line in alpha plus beta region would look something like this, and if I draw the diffusion path, it may be something like, it may look something like this. First it passes through alpha 1, then it passes along the tie line, and then it enters beta region, and then it enters the beta region, this. So, the diffusion path may look like this, with the segment within, with its segment within the two phase region being parallel to a tie line or along a tie line. This is important because a tie line represents equilibrium compositions of the two phases in equilibrium, and hence we can determine the equilibrium compositions of the two phases at this temperature, or essentially by determining the composition profiles we can determine the tie line of the alpha plus beta two phase field. So, if I draw the concentration profile here, let us say for B it may look something like this, and these two compositions Cb alpha and Cb beta are basically the equilibrium compositions given by these tie lines, given by this tie line. So, this helps us in determining the phase diagrams. Second rule, if a non-planar interface forms between two single phase regions, or if there exists a two phase region in the diffusion zone, it indicates that the diffusion path is passing through the two phase region across the tie lines. So, you can write if a non So, if I assemble a couple between beta 1, the tie lines in this would look something like this, and if the diffusion structure shows a non-planar interface between alpha and beta, or two phase region so this is basically two phase region is a mixture of alpha and beta phases. Obviously, as we go towards beta rich side, the beta precipitates, the density of beta precipitates will keep increasing. So, the matrix here in this two phase region is alpha, precipitate is beta. So, in any of these cases we expect that the diffusion path will cross alpha plus beta region across the tie line. So, if we draw the diffusion path, it may look something like this. So, basically the segment of the diffusion path within the two phase region is across the tie lines. So, that means there is no equilibrium between alpha and beta, and with this we get an idea about the phase boundaries, but we will not get an idea about the tie lines, but still these structures would be helpful. Then the third rule says if there exists a planar interface between two phase layers in a ternary diffusion couple, it indicates that the diffusion path is passing through a tight triangle. Obviously, when there are two phase layers, for example, here let me write it down first. So, suppose if diffusion couple is assembled between, let us say, alpha 1 and gamma 1, alpha and gamma. What this says, there exist two phase regions and there is a planar interface between the two phase regions. So, there will be a planar interface and on two sides there will be two phase regions. So, obviously, within the two phase regions there have to be three phases, there cannot be four phases, because it is not possible based upon the Gibbs phase rule. A four phase layer or a four phase equilibrium in an isothermal ternary diffusion couple is not possible. So, this may be alpha plus beta on one side and alpha plus gamma on the other side. So, if this is the case, we can see how the diffusion profile will look like. So, first the diffusion profile has to be in the alpha phase region and then it is entering alpha plus beta two phase field. It will pass like this, then it will enter alpha plus beta and then it is going into alpha plus gamma region. So, it has to pass through this ternary triangle, then it passes through alpha plus gamma region and finally enters the gamma phase field. So, this is how the diffusion path may look like. Obviously, since there is no direct interface between alpha and beta here, so within the alpha plus beta region the diffusion path has to cross across the tie lines and hence this interface is non-planar. Similarly, as you can see, as the diffusion path is entering from the tie triangle side and then entering into gamma region, so the diffusion path again has to pass through the alpha plus gamma phase field here across the tie line and hence the interface alpha plus gamma and gamma, the interface between alpha plus gamma and gamma should also be non-planar. So, this is how we can get an idea about phase diagrams and their features based upon the diffusion structures developed in multi-phase diffusion couples, and this has been used by our group for developing phase diagrams or getting information about phase diagrams, including aluminum, magnesium and even in the quaternary system of iron, nickel, cobalt, copper. Now, next question is, how do we analyze the multi-phase diffusion profiles for interdiffusion fluxes and interdiffusion coefficients? So, that we will cover in the next class. Thank you.